In looking at Electrochem Part 1, quick check. We have a context of a fuel cell. We have methane, alright, as a fuel for fuel cell. So in this case, methane, from this equation, it's likely methane is a starting reactant, and therefore it has to undergo oxidation to form O2. So your methane electrode will therefore be your anode. The oxygen electrode will therefore be your cathode, and where this is where your reduction occurs. Okay, so I've the E naught of this equation is given. I've taken reference to the booklet to get E naught of the reduction of O2 to H2O. Alright. So take note, we are using an acidic medium. So we are supposed to look at the data booklet to calculate the standard cell potential of this fuel cell. So this will be my E naught reduction, because reduction is occurring here. This will be my E naught ox. To apply the formula, E naught reduction minus E naught oxidation. Sub in the values 1.23, subtracting positive 0.17, and therefore you get 1.06 volts. Okay, to calculate the standard Gibbs free energy of this fuel cell, we make use of this formula, delta G naught equals to negative NF E naught cell. Quick recap of concepts, this delta G will be in J per mole. Okay, because of the formula, alright, your Faraday is coulombs per mole. E naught cell is voltage. When you multiply coulombs per mole to voltage, you get J per mole. Alright, so N is the number of moles of electrons being transferred per mole of reaction. So when we take a look at this reaction, number of moles of electrons being transferred will be 8 electrons. Okay, so N in this case equals to 8. Sub in your 8 for your N. Faraday constant 96500. E naught 1.06 volts. Substitute in, as I mentioned earlier on, you will get a units of J per mole. Delta G, typically we will express in kJ per mole. So to convert to kJ per mole, we divide by 1000. Okay, that's how we get negative 818 kJ per mole. Okay, moving on. We are supposed to draw a fully labeled diagram of electrochemical cell we could use to measure this E naught cell. Okay, so basically this E naught cell consists of two half cells. One is the methane CO2 half cell. So it's important for us to know what's this half cell. This half cell involves CO2 gas, H plus aqueous, CH4 is a gas, methane is a gas, and water is a liquid. So you can see we have a gas ion half cell. Okay. As a result, for this half cell, we will need an inert electrode called the platinum electrode. Alright, CH4CO2. Alright, so both CH4 and CO2 has to be present. So both of them present at 1 bar, 298 Kelvin. As I mentioned, we need the platinum electrode as the inert electrode. And in this case, what are the species present? The ions, H+. So H+ must be at 1 mole per dm cube. So that's done for one half cell. That's the methane CO2 half cell. So some of you may be confused, right? You may think that, oh, sure, CH4 is the reactant, CO2 is the production, but CO2 be taken out. So in this case, for a half cell to work, you need to have both species to be present. So both methane and CO2 needs to be present in order for this half cell to work. And that's why, in this case, both methane and CO2 has to be pumped into the gas cell. Okay, moving on, we then look at the other half equation, which is the O2 getting reduced to water. So in this case, O2 is a gas. Of course, H plus is aqueous, and then H2O, it's a liquid. So again, we have a gas ion half cell. So we need a platinum electrode. So in this case, the gas that needs to be pumped in will be O2 gas. Standard condition, 1 bar, 298 Kelvin. As I mentioned, you need a platinum electrode, inert electrode, and then the ions present will be your H+. Okay, at 1 mole per dm cube. So that will be your standard condition. So once you have your two half cells ready to measure this E naught cell, we therefore need to have a high resistance voltmeter. And to complete the circuit, we need a salt bridge. So things to take note. Important, draw in the water level in the solution level, the electrolyte level in the gas subcell. Okay, and then your salt bridge typically drawn with an open end. Okay, of course your voltmeter to measure the reading. Okay, so 3 marks, check you're working for this. You can mark yourself accordingly. So recall again, common confusion among students was that they thought that CO2 was a product in this case, and therefore it needs to be pumped up. So as I mentioned again, in the half cell, both species must be present in order for it to work. So both CH4 and CO2 should be going in. Okay. If not, then we look at number 2. Number 2, we have another system. We have a zinc 2 plus zinc half cell and a manganate Mn2 plus half cell. So I've taken the liberty to copy out the data booklet half equation involving the species, so color coding for ease of referencing. Okay, so in this case, the overall EMF was calculated to be 2.28 volts. So in this case, we can take a look at the E0 values. So E0 value is 1.52 volts, E0 value is negative 0.77 volts. So since this E0 value is more positive, this will undergo reduction and this will undergo oxidation. So in this case, we can make use of the E0 value to check, alright, which is the likely to have the reduction reaction, because in this context, I have both manganate and manganate. So it's a half cell, alright. It is unlike a situation when you're just given only one species of the both, right? In this case, the direction of the reaction is fixed. Similarly, for the zinc 2 plus zinc half cell, both species are present, and therefore I need to consider whether it undergoes oxidation or reduction. Okay, so in this case, reduction for manganate, oxidation for zinc. Okay, and then the question says, now we have this system. Of course, we can do a quick check to calculate the E0 cell. E0 cell will be equals to 1.52 subtracting negative 0.77, and that's how you end up with positive 2.29 volts. Okay, so it's somewhat near 2.28 volts. Okay, so now what's the question asking? The question is asking for a disturbance. So you can see this half cell was electrochemical cell was perfectly fine. What we did was we now added in some zinc nitrate. So in this case, zinc nitrate is a salt. It contains zinc 2 plus. So what happens is that zinc 2 plus concentration will increase. The question asks you what happens to the feasibility of the reaction. So feasibility of reaction, we look at therefore delta G0, and we know that in electrochem delta G0, the proxy is also your E0 cell. So addition of zinc nitrate, first thing first, increases zinc 2 plus. And now, therefore, it becomes a question on Le Chatelier's principle. When zinc 2 plus increase in concentration, let me remove this arrow. Okay, the equilibrium position of number 1, alright, we'll now shift to the right to decrease zinc 2 plus concentration. So that's your LCP concept. Now we need to apply our electrochem concept into this to layer in the concept. So in this case, because reduction is favored, the forward reaction is reduction. Alright, E0 becomes more positive, and in this case, because we're looking at oxidation, E oxidation becomes more positive. So since E cell equals to E reduction minus E oxidation, if E oxidation becomes more positive, you are subtracting a more positive number, the E cell will therefore become less positive, and this will result in a value that's less positive than 2.28 volts. And since if E cell is less positive, we know that E cell positive, it's more spontaneous. So if it's less positive, it means it's less feasible. Okay? So therefore, feasibility of the reaction decreases. Okay, and that concludes quick check 1 of Electrochem 1.